Hey friends, how are you? And in this video, I'm going to discuss about a very important reaction, and this is a favorite question for any type of competitive exam. It may be your CSI exam or GATE exam, but it is a very favorite question, and this is nothing but a cycloaddition reaction involving a aziridine ring and an alkyne. And the reaction is composed of two reactions. Both are pericyclic reaction. One is electrocyclic ring opening reaction, and another is cycloaddition reaction. So let's start the reaction. So as you can see, these are the compounds or the starting materials given. So both of these are aziridine rings, and this is phenyl ring. You can see here it is also phenyl ring. For the light, it may not be visible, but it is phenyl ring. And for along with this aziridine, there is given a alkyne, and it is heated. So what will be the products? And as you can see, the starting material in these two cases are different, and as I told previously that it is pericyclic reaction, one is electrocyclic reaction and one is cycloaddition reaction. So the two products will be different in these two cases because the starting materials are different, because pericyclic reactions are stereospecific reactions. So you can see in this case, in the first case it is cis aziridine, whereas in the second case it is trans aziridine. And what I mean by cis and trans aziridine is that the substituents are cis or trans. The aziridine ring cannot be cis or trans because a three-membered ring should always be cis. Ring junction cannot be trans. Okay. Now, so first let us talk about little about the aziridine ring. So whenever you have a aziridine ring like this, any form, so these aziridine rings are not unstable. They are fairly stable. When you heat them, no reactions will occur. But when you have any electron withdrawing substituent in the aziridine ring, as in the case here, then the ring becomes unstable. Why is that? Because then the nitrogen lone pair can push and this bond can easily break because it is stabilized into this carbonyl group. So what you will get, you will get a double bond here, and along with that a stabilized enolate. So this is why this type of aziridine rings are unstable with respect to heating. Now in the reaction which is given here is that, so let us first take the case of this uh, cis aziridine. So when you heat it, what will happen? This ring will break. So nitrogen lone pair will push and this ring will break. Now this ring, so this is a ring opening reaction, and this is not an ordinary ring opening reaction. It is a electrocyclic ring opening reaction, and you can see in this particular electrocyclic ring opening reaction it involves two electrons. So two arrows are there, that means 2 plus 2, 4 electrons are involved. And although I didn't talk about electrocyclic ring closing or ring opening reaction, I will mention here shortly that whenever you have 4 pi electron in your electrocyclic ring opening or closing, it will be con-rotatory, and whenever you have 4n plus 2 pi electron, it is, so actually it is 4n pi electron, it is con-rotatory. Whenever you have 4n plus 2 pi electron, it is dis-rotatory. Given that the reaction condition is heating condition, that is thermal condition. If it is photochemical reaction, then it will be then it will be reversed. That is, for foreign system that will be dis-rotatory, and for 4n plus 2 that will be con-rotatory. But here it is thermal reaction, so we will follow this rule that 4n condition, 4n pi electron is con-rotatory. And you can see 4 electron means n equal to 1, so it is a 4 electron means a 4 pi n electron system, and that means the ring opening will be con-rotatory. Now what is mean by con-rotatory or dis-rotatory? So here I will draw the hydrogens also, which are at the back side, and now I will put one arrow from here along this bond and one arrow from here along this bond. And now con-rotatory means whenever this ring will open, it can either open that this bond will rotate like this, and this bond will also rotate like this. That is, either both should be clockwise, or both can be anti-clockwise. That is this is also anti-clockwise or this is also anti-clockwise. So this is called con-rotatory. So whenever you have a situation where you are closing you are opening a ring or closing a ring, and if you have a ring rotation like both are clockwise or both are anti-clockwise, then it is con-rotatory. But whenever you have a situation like this where it is clockwise but it is anti-clockwise, then it is dis-rotatory. Or it may be it is anti-clockwise and it is also it is clockwise and it is anti-clockwise. That is, if both are clockwise, that is both are in the same side, then it is con-rotatory. But if they are in the opposite side, then it is dis-rotatory. So in this particular case, as predicted by the Woodward-Hoffmann rule, that is for foreign system, this is con-rotatory. So let's say we consider this rotation, that is it is rotating in a in a clockwise manner. So after the breaking of this bond, what we will get, this. So you can see if it rotates in a clockwise manner, this CO2 Me group, which is like this, it will go like this. So it will go here, CO2 Me, and here you will have the hydrogen. And for this one, so it is clockwise, that means it is above the plane and it is rotating this, so it will be inside the ring. Sorry, it is CO2 Me. So you can see, so as they are C's in the starting material, these two groups are C's. So when they rotate in the same direction, that is both are clockwise, after rotation they will also be in the same direction. That is, it is going this right hand direction, it is also in the right hand direction. So this is the result of your con rotation. Now you can see this is a dipole, 1 3 dipole. This is 1 2 3. So this is, we can write it like so, positive charge we can also represent here. So this is clearly a dipole, and you can see this is a resonance stabilizer. The full thing is in resonance, and that's why, although this particular side where it is negative charge, so this side we can say that it is in resonance, there is a double bond is there, that's why the rotation is not possible and it is fixed in this particular configuration. But in this case you may think that it is a negative charge, so it may rotate, but you are putting your other component, that is this alkyne, in the same pot, and that's why it will not allow any rotation to occur and it will react in the form as it is. And when a cycloaddition will occur, you will get a product like this. So a 5-membered ring will form. Now I am considering that this 1,3 dipole is in the plane and this alkyne is approaching above the plane. So if it is in the plane, you can see this inner substituent, this CO2 Me group will obviously go downward, that is CO2 Me. So actually I shouldn't write it like this, I should write it like this, hydrogen. They are in the same plane. They are in the same plane. It is not that hydrogen is below the plane. This, all the things are in the same plane. We can consider a plane of symmetry throughout the molecule. And after reaction, you can see this is inner substituent, so it will go downward and the hydrogen will go upward. Here you will have the phenyl ring, here you will have the double bond, and in this case this hydrogen will go downward because it is inner substituent, and this CO2 Me group will go upward. So this is the product which you will get from this cis isomer. But now consider the trans isomer. Trans isomer means you will have these two groups will be altered. That is, now you will have hydrogen here and this CO2 Me group here. So here you will have hydrogen and here you will have CO2 Me group. So if the same things occur in this case, you will get this CO2 Me group here and the hydrogen here. Okay, so what we get is that when we use the cis isomer after the reaction, so when we use the trans isomer, that is the trans aziridine, the substituents are trans in the starting material, in the product they are cis. So when we use the trans starting material, we get the cis product From trans we get cis, whereas from cis we get trans. So this is very important. They will give you a lot of options, cis, trans, or other things, but you have to predict which will be the right. Sorry for one thing that I forgot to mention is that here you will have this CO2 Me group, but but it doesn't matter because it doesn't have any stereochemistry. It is in the plane. So this is all. This is a very uh, I important question for CSIR exam, and I hope that I am able to explain it to you, and that's all. So thank you for watching and best of luck.